So the next talk we have, it's Federico De Marche, as I was very carefully educated in the naming, on the unlocking of superior performance in reconfiguration data center networks with credit-based transport. Federico is a third-year PhD student in computer science at the Max Planck Institute for Informatics. He is advised by Yiteng Xi, earned NMSc at Saarland, and he is currently focused on re-architecting the network stack for future data center architectures, but is not immediately available for the job market. Thank you very much.
Thank you for the introduction. I am Federico, and today we will introduce how we designed a high-performance transfer protocol for reconfigurable data center networks. But first, let's see what reconfigurable networks are. So, for the past decade, data center networks have been built as hierarchies of electrical packet switches, which we informally call clone networks. However, due to the slowdown of Moore's law for networking, these same electrical switches are becoming the bottleneck of this clone architecture, making it costly to build and inefficient to scale. And this motivates the shift to alternative switching devices. And this is why the industry and researchers alike have started integrating optical circuit switching into data center design. These switches offer high switching capacity at a low cost. In this figure, we see two optical switches connecting A nodes, where nodes can be anything ranging from electrical, top-of-the-rack switches, to individual servers, or even just GPUs. At a given moment in time, which we call a time slice, our nodes are connected pairwise by a set of high-bandwidth circuits that from now on, for ease of visualization, we represent as edges between these nodes. In order to change this set of circuits, our optical switches have to go through a reconfiguration process, which brings the switch down for some time and then results in a new set of circuits. And this is why we call this a reconfigurable network. Now, the time it takes for these switches to reconfigure is quite an important parameter for network design. This is because how we design a reconfigurable network depends on the reconfiguration frequency of the underlying hardware. And while higher reconfiguration frequency will typically lead to more theoretically optimal designs, they will also be more difficult to realize in practice. Nonetheless, just last year, a microsecond switching architecture has been realized and demonstrated in practice in a full end-to-end system, in the RotorNet Opera architecture. And this is going to be the focus of our work. So how does this network function? So at this time scale, reconfigurable networks are what we call traffic oblivious. This means that in order to deal with arbitrary traffic patterns without the need of fine-grained measurements, our circuit switching schedule is pre-computed in advance so that all nodes get a direct connection to all other nodes in some time slice, which emulates a complete graph over time as this cycle of configuration repeats. Now, microsecond switching is very fast, but it is not fast enough to grant timely connection between all these nodes, especially as the scale of network grows. If we were only to wait for direct circuits, we would disrupt general data center traffic, which is often sensitive to latency. And this is where the Opera architecture comes in. Opera proposes to build the reconfigurable network as a time sequence of expander graph topologies, which individually have great connectivity properties. And we call the time sequence of these expanders a varying expander topology. In order to avoid disruption due to circuit reconfigurations, only a subset of the circuit switches is reconfigured at the same time. So, for example, in this transition, only the yellow circuit will first go down, while the red and blue one keep up the network. Then only once the yellow circuit is back up, we can also reconfigure, for example, the red ones. And this approach guarantees that our traffic can always flow through any pair of nodes at any moment in time, even as the network reconfigures. So this varying expander network we just presented has some great properties in theory, promising to achieve high throughput at low cost, even if only using these multi-hop paths because of the great properties of the underlying expanders. However, this was not the case in practice in the original evaluation of Opera. In the original evaluation, the varying expander would only deliver half the throughput of a cost-similar clone network under some adversarial traffic scenarios. And we attribute this performance gap to the lack of a suitable transfer protocol. The NDP transfer protocol, which was used to couple with the Opera evaluation, was actually designed and intended for clone networks. So it is actually unsuitable for it, which leads us to our main question, which is, how should we design a transfer protocol for varying expanders? It's quite difficult to handle traffic in dynamic network in practice, so what can we learn from existing transport solutions, and why are those solutions still yet not sufficient? So the majority of transport protocols are what we call reactive. In reactive transport, a sender will send a certain amount of data into the network and then adjust this amount of data via continuous feedback loop from a receiver until it finds the bottleneck bandwidth. The problem with this approach on a varying expander is that a particular graph configuration will not persist for long enough for us to gather sufficient information via feedback, which makes this approach quite unreliable. An alternative paradigm of transport is what we call proactive transport, which explicitly schedules data in advance. And a prominent example of this is credit-based transport. Credit-based transport uses the opposite approach. It is receivers that send credit packets to senders that upon reception trigger the transmission of data. And as it is the receivers that control the rate of credit, this approach should guarantee congestion-free data paths without the use of a slow feedback loop, making this approach quite desirable for our varying expander. However, the majority of these credit-based solutions assume that the network has a single bottleneck link at the receiver downlink, such as in fully provisioned echelon networks. And one example is NDP, which was used in the evaluation of the varying expander. However, the varying expander is at its core a multi-bottleneck topology. So controlling the rate of credit exclusively with the receiver will not control congestion. In this example, we see two senders and two receivers for two separate credit flows, on a simple dumbbell topology. What's going to happen in the majority of credit-based transport is that this receiver, based on the local view of their bottleneck, will simply locate the maximum amount of credits to the sender. This credit will simply pass through the bottleneck, and then the sender will send double the expected amount of data through the bottleneck link, which causes congestion. A solution to this was proposed by the transport protocol called ExpressPass. In ExpressPass, credit flows through separate rate-limited credit queues. This means that even if we were not to change the amount of credit allocated from the receiver, now the intermediate bottleneck will drop the excess credits, resulting in the correct amount of bandwidth eventually being allocated by senders. And this approach is a great start for us because it allows us to do credit-based on multi-bottleneck topologies, such as our expanders. But it still comes with two major challenges that we need to overcome. First of all, credit data paths must be symmetric, meaning that data packets have to follow the same reverse route as the corresponding credit, or we will still have congestion. Then, the waste of credits, which is generated by these additional intermediate bottlenecks dropping credits, must be minimized, or we will have low link utilization. And as our network is reconfiguring at microsecond scale, these are actually very difficult to solve in practice, which is why we designed Flare. Flare is a multi-bottleneck credit-based transport for this varying expander topology. In Flare, Flare's design is rooted in solving these two main challenges, with some additional optimization in terms of both latency and throughput. For reason of time today, we will focus on the second challenge of minimizing credit waste. This is Flare's main performance driver and is what makes it quite unique. In our paper, we also show how to guarantee path symmetry even across a changing topology by leveraging the routing of Opera, which enables us to do credit-based transport to begin with. In our evaluation, we showed that Flare achieves double the throughput of NDP, and this means that Flare combined with the varying expander actually achieves higher throughput than across similar clone network, even under adversarial traffic. For the remainder of this talk, we'll take a deeper dive into our take on the credit waste problem and then show some key result evaluation points. So what is credit waste? When credits compete on multiple bottlenecks, they can generate what we call credit waste. In this example, we have 3 credit flows sending at a maximum credit rate competing across 2 bottleneck links. As we saw earlier, what is going to happen is that the A to B and A to C flow will each see 50% of their credit dropped at the first link to maximum capacity. Then the remaining 50% of the A to C flow will compete with 100% of the B to C flow, resulting in a 67 to 33% share. And pushing fairness aside, we have just generated credit waste. If we look at the resulting allocated bandwidth end-to-end, we will see that we only were able to allocate 50 plus 33% worth of bandwidth for the first link, which makes it underutilized by 17%. And this is quite a common problem in credit-based transport. So previously, ExpressPass dealt with this problem by having these credit flows converge to a fair credit sending rate using a reactive feedback loop, which also minimized credit waste, as in the figure. The problem is that, as we stated earlier, a reactive feedback loop is most ineffective on a changing topology. And so this type of convergence is mostly out of question. We need a different strategy. What we propose is to use a simple stateless heuristic. Let's say we only add link local immediate information at our first bottleneck link, such as the route of our credit flows. Now, which of these credit flows we deem least likely of generating credit waste? Well, that would be the credit flow on the shortest path, because it has fewer potential bottleneck links remaining to its destination, meaning fewer chances of getting its credit dropped. So our overall strategy is going to be that we want to admit credits with fewer hops remaining to the destination more frequently than the others. This intuitively, on a particular graph configuration, will probabilistically minimize credit waste. But at the same time, of course, will also be inherently unfair to flows on longer paths. But our key consideration here is that the varying expander reconfigures a microsecond scale emulating a complete graph, meaning that all nodes get a short path to all other nodes quite uniformly in the schedule, meaning that fairness can still be achieved on the longer term. Now, how we go implementing this idea, though? So we propose how to implement Flare in programmable switches. In Flare, credit packets embed the remaining hop count in their packet header, and then the credit queues that host these credit packets use this remaining hop count to only selectively admit these credits. Before a certain credit queue threshold, all credit packets are admitted, regardless of their hop count. As the queue grows, after this threshold is crossed, credit packets are admitted only probabilistically based on their hop count, with lower remaining hop count leading to a higher admission chance. And this means that under contention, as the credit queue is growing, it will start holding more credit packets with fewer hops remaining, which will probabilistically diminish credit waste, at least locally for the link, for future credit packets. So this was pretty much our base idea on how to minimize credit waste. Next, we'll go through some of our related evaluation to see some key points of this idea. So we evaluate Flare in both large-scale simulations and small testbed experiments. For this talk in particular, we'll show some results reproducing the original Opera simulation setup. In particular, we want to see whether Flare is actually fair on the long term, whether it actually achieves lower flow completion time than comparable state-of-the-art baselines, and then finally whether Opera compared with Flare can achieve higher throughput than a cost-similar flow network. So to start with, we show that Flare is fair on the long term. For this, we ran quite a common fairness test. We ran 4 flows in a 4-to-1 incas pattern, starting and finishing at an offset, and we sampled the throughput at the duration of a cycle of configurations, which is the time scale we expect Flare to be fair at. So we plot bandit share on the y-axis for each flow and over time on the x-axis. And we see that, as expected, Flare is reasonably fair on this longer term, as the bandit share of this flow is mostly overlapping. This is possible because, by construction, this varying expander network offers quite uniform node-to-node average path length across the sequence of expanders, which makes probabilistic credit location quite fair on the whole length of a cycle. Next, we compare Flare against other state-of-the-art baselines in terms of flow completion time. For today in particular, we see traffic from the previous Opera paper at high load, and also based on the same time slice duration of 55 microseconds per time slice. In this plot, we see on the y-axis the flow completion time for flows of different sizes on the x-axis in the trace. And we see that Flare in black overall achieves the lowest latency out of all baselines. The second best baseline is Bolt, which is a reactive transport which uses sub-RTT feedback from programmable switches to deliver very fast feedback, which makes it quite competitive in this scenario, actually. However, as we decrease the duration of our time slice to 15 microseconds to make our network more dynamic and the cycle shorter, we see that now the gap with Bolt actually widens. And this is quite an inherent limitation of reactive transport. As the network gets more dynamic and changes more often, it is more difficult to control traffic reactively, of course. As a final experiment, we reproduce one of the original experiments from the original Opera paper. In this experiment, the same varying expander was compared against a cost-similar flow network under the adversarial scenarios of all these flows using the least bandwidth-efficient multi-hop paths. And this resulted in the flow network having double the throughput of this varying expander. We now reproduce this experiment with Flare rather than with NDP. So here we plot throughput on the y-axis over time on the x-axis. And we finally see that Opera, combined with Flare, achieves higher throughput than the cost-comparable flow network combined with Bolt, which we found to be the best algorithm for it. But the more interesting thing is that the traffic load we input is 35%. So this traffic input, in theory, should be beyond the optimal throughput of each individual expander in Opera. The reason that Flare can go beyond this throughput is because our probabilistic admission, as the network saturates, will start admitting credit with fewer hops remaining, meaning that it will steer traffic towards shorter paths across the sequence of expanders, rather than considering the individual ones, which makes this varying expander have higher throughput than Clo even when traffic is more adversarial. This exploits a unique property of reconfigurable networks where it is actually possible to wait and sacrifice some latency to wait for a shorter and more bandwidth-efficient path, which makes this network capacity increase overall. So to summarize, we presented Opera's varying expander, which has great properties in theory and also has been demonstrated in practice just last year as implementable. So the rotor switches were actually implemented in practice. But to perform optimally, it needs a different transport protocol than normal static networks, which is why we designed Flare, which is a dedicated transport protocols for this varying expander network, which enforces credit data symmetry even across changing topologies and is able to boost its throughput to probabilistic admission. In contrast with the original paper, we showed that Opera, combined with Flare, can achieve higher throughput than a cost-similar Clo network, even when traffic is adversarial. Thank you for listening, and I'd love to take questions.
Questions from the floor, please. So if we could just ask you to stand up, then you'll get a mic.
Of course. Thanks a lot. So thanks for the really interesting presentation. I had a question. How is this the threshold set to which you're dropping the credits for the probabilistic admission, and if it's something that's static or depends on the application? Thank you.
Great. So in our evaluation, we just set a static 50% threshold. The overall, the reasoning behind setting a threshold would be that as your overall traffic increases, you will want your threshold to be possibly lower to also increase your network throughput. The threshold is a representation pretty much what portion of the packets in the queue will be affected by probabilistic admission. So if you're expecting a high traffic load, maybe you would want to set a lower threshold, but maybe for lower traffic operation, we may want to set a slightly higher threshold so you can don't risk having possibly lower utilization. But for this paper, in evaluation, was just set to 50% of the queue.
Super.
Thank you so much.
Sure, thank you.
Further questions from the floor? Was there one at the back there? Yes.
Great talk. I really liked it. One thing about the credit wastage, how do you contrast your approach to other approaches in the community which have taken, like, say, overcommitting credits?
I think I missed the middle part of your question.
How do you contrast your solution about probabilistically admitting credits to overcommitting credits?
Well, it's a random graph, so randomly admitting credit was a good idea. But aside from that, the probability of credits does reflect the chance it has, assuming the worst case scenario of all bottlenecks having flow competing, then the probabilistic admission will tell you if you have 4 or 5 hops remaining, then at each hop, your chance of getting to the next hop will diminish by the number, the number of flows. So in theory, it's trying to predict if the credit packet can get through without getting lost. Because as this credit packet travels several bottlenecks, it consumes bandwidth. So it is costly to transfer traffic across several bottlenecks. So this probabilistic admission is kind of a stateless method to try and predict whether will this credit packet make through if there is contention. So if I detect contention on my first link, I think, okay, there's probably also contention maybe on the other links, so I try to drop it early.
Okay, thank you.
Okay, we could thank thank the presentation.
Thank you.
Thank you, Federico.